Hi guys, welcome back to Learn Electronics Repair and the next video in the series Learn Electronics for Beginners and Everyone. So if you're following the series, you know in the last part we had a look at inductors, how inductors actually operate in a circuit. We did some practical demonstrations to show that they actually generate a magnetic field, and when the magnetic field collapses it generates voltage, it converts back into voltage, and we got rather a lot of voltage out of our experiment. So if you missed that, go watch the previous one. If you did watch that one, well, let's just continue. So often with electronics, the easy way to explain things is with the analogy of using water. We did this with resistors and capacitors, so let's do it again with inductors, because it may seem strange effectively that you can apply voltage to one end of a coil but the voltage doesn't automatically immediately appear on the other end of the coil, even though it's just a coil of wire. The DC resistance is practically zero. So what's happening? Well, in the world of water, we can explain this best as a water wheel. I've done this analogy before. If you've seen this, skip forwards a bit because there's plenty of new stuff in this video. But for now, let's look at the water wheel analogy. So with the water wheel then, we have a water inlet. We have our water wheel. We have an outlet, like so. And we have the wheel vanes, if you like, okay, paddles, whatever you want to call them, on our water wheel. There we go. So what happens when we feed water into our water wheel? Does water come out straight away? No, it doesn't, does it? There's water going in, current, yeah, there's current going in, but there's no current coming out yet. Why? Because the water wheel has inertia, it's heavy, okay? The water wheel has to start spinning, and it takes a little bit of time to do that. So as we apply pressure here, the water wheel starts to rotate, and after a little while this effectively is filling with water, and some water starts to come out here, and the wheel gets faster and faster and faster, and eventually it reaches the point where it's spinning at full speed, and the amount of water flowing in equals the amount of water flowing out. So we now have an equal amount of water in and out, okay? What happens if we stop flowing water into it? Does it just stop? Does water stop coming out straight away? No, because the water wheel has inertia, as I mentioned, so it has to slow down, and while it's slowing down, water is still coming out, although there's no more water going in, and the amount will decrease and it will stop after a period of time. Okay, now this is important when we come to electric current, because while the current is flowing in and the water wheel is spinning up, where's the high pressure? It's here, yeah, the high pressure is here, and the low pressure is on the output. What happens when the water wheel gets up to full speed, so that the amount of water flowing in equals the amount of water flowing out? Well, at this point the pressure on the input equals the pressure on the output. They're in balance. There's no pressure differential across the water wheel, water pressure, it's the same. What happens when we reduce or we stop feeding water in? The wheel is still spinning, water is still coming out. Where's the high pressure now? Well, it's here on the output. The high pressure of water here, and this is now low. So you can see that during the cycle of this spinning up and spinning down, we go from a condition where we have high pressure on the input, low pressure on the output, to an even amount of pressure, to low pressure in the input and high pressure on the output. And the same applies with the inductor coil. So with our inductor coil, and just to reply to comments via a few people on the first video, the former that I called it, which the coil is wrapped around, either metal plates or ferrite, it's a magnetic powder mixed with ceramic. I called it a former, but it's actually should be called the core. Okay, so it's a ferrite core, that's the correct term. Sometimes you'll use the word bobbin, which effectively means the winding. I think it's a bit semantic and it doesn't really matter. I think we all know what we mean anyway. But core is the thing that it's wound around, okay? Now let's apply some power to our coil, okay, by closing the switch. So this is ground, 0 volts, this is 12 volts. What happens when we apply power? Well, current starts to flow into the inductor like our water wheel. Does the current flow in and out at the same time? No, this has electrical inertia. What happens is the current actually goes into the magnetic field. Energy cannot be created, nor can it be destroyed. Energy can only be converted from one form to another, okay? So the energy, the current flowing in, is used to build up the magnetic field. And this happens when we close the switch. Okay? What will happen after a period of time is that the core will fully magnetize. At this point, all the current flowing in will equal all the current flowing out. It can no longer magnetize further. At that point, you'll end up with the full voltage across the coil, okay? What happens when we open the switch? Well, we know what happens when we open the switch because we tried it in part 1. Yeah? We still have 12 volts on here, and all of a sudden we open the switch. No more current can flow through our coil. So the magnetic field collapses, and in collapsing, it generates a high pressure on this end of the coil. Like this, when we stop the water coming in, the water is still flowing out. The high pressure is now here. So what it actually does is increases the voltage. The voltage here is already 12 volts. That's our power supply. That doesn't change. So the voltage here has to go higher than 12 volts. Okay? How high does the voltage go? Well, that will depend in particular on the resistance from here to ground. Now, we connected our oscilloscope probe here, and this is 0 volts ground, and here. So our oscilloscope was connected to there, and our oscilloscope internally has a resistance, and it's around 10 mega ohms. 10 mega ohms. So we can imagine this circuit effectively as being that. That's the resistance of our oscilloscope. So we do have a current path to ground, okay, through a high value resistor. So the voltage here will increase at this point until it can find a current path. Now we have a 10 meg resistor here, so current will start to flow, but only a small amount of current can flow through there. So the voltage here increases to the point at which it arcs across the terminals. The air itself breaks down and passes current. And that's why we can see sparks in the switching contacts. It's not the current. Remember, this was drawing something like 0.08 amps because of the resistance of the winding. So we're not like having a massive current in there, it's the voltage across it. So what would happen then if we didn't connect our oscilloscope here? What would happen if we connect our oscilloscope like this? So the same circuit, no, drawn it wrong, a similar circuit, So we now put the switch here, okay? And then the coil, this is 0 volts, this is 12 volts. And we connect our oscilloscope from here to here. So we're measuring the voltage across the coil. Yeah? There's no longer effectively a 10 meg resistor across here. Well, let's try it and let's see what happens, and then we'll come back and talk a bit more. So there is our relay. Let's switch this on. Well, we've certainly got some bigger spikes. I've just captured one there. So we now have 580 volts, even more. Notice the waveform is now upside down effectively, because I'm now taking the ground from the other end of the coil rather than the other side of the switch. Yeah. And there we have 580 volts. Yeah, plenty of volts there coming out of the coils. So you've just seen we got even more voltage across here. Before was about 510 and now it's like 590 practically. We get more voltage across here. Why? Because there's no longer a current path through our oscilloscope. The current's got to go somewhere, yeah. And basically the voltage at this point will increase to a sufficient point to form a current path. That was the breakdown of the air in between. So we would actually get bigger sparks if we could see them very well. And we got a higher voltage there. So that's proven that when we open the switch, the voltage at this end of the coil will go up and up and up until it gets a current path. It has to go somewhere. Energy cannot be created nor destroyed, and it doesn't kind of like hang around sulking in the corner, yeah, until you connect the switch again. No, it goes somewhere, and that's where it's going, across the switch. Now I want to tell you something that's so obvious you'll always wonder why you didn't understand this. We know, because we've proven this, that when we apply current and we build up the magnetic field, once we stop the current flowing in, we open the switch, the magnetic field collapses. And when the magnetic field collapses, it generates a voltage in the same direction the current was flowing in the first place. So the voltage at this end goes up. We've seen that, yeah? And it will go up until it can form a current path. Now, when we created the magnetic field, let's go rewind a little bit. When we created this magnetic field, we also created a voltage in the magnetic field, if you like. So imagine this, when the magnetic field collapses inwards, the magnetic field is passing through the winding in that direction. And that's generating a voltage in the same direction, the same polarity as the original voltage. Okay? Look, you know where this is coming from now if you're just thinking a step ahead. When we magnetize the coil, the magnetic field is passing that way through the winding. And that generates a voltage as well. But it generates a voltage in the opposite direction to when it's collapsed. So what actually happens is, in reality, when we apply a voltage on here and current starts to flow in, the magnetic field generates an equal and opposite voltage to effectively counteract the voltage you're applying. So as the voltage here goes up, this magnetic field in building is creating an opposite voltage, pushing it back down again. That's why actually you don't just get the voltage appearing at the other end of the coil. Yeah? So that's why it actually behaves this way. That's why you don't effectively get the full voltage across the coil. Yeah? That's clever. Once you realise that, all this becomes very obvious, and you can get from the water wheel to the magnetic field. It all makes sense, I hope. Yeah? Okay, so we can see effectively that the inductor tries to counteract any change in current. So if you increase the current in, which increases the size of the magnetic field, it automatically generates a reverse voltage to decrease the current again. Yeah, the potential difference between the two decreases, less current flowing. So what this actually means is, until we reach the point of saturation, an inductor will pass DC, but it will block AC. That's what's really happening here. It's passing DC, and until it saturates, it blocks AC. Once it's saturated, well, it's just a piece of wire. Think of AC as a change in the direction of current. So each time the direction changes, the magnetic field switches from one polarity to the other and continually tries to counteract the current that's causing it to change. This is why that's happening. So this is opposite to a capacitor. Yeah, a capacitor passes AC, blocks DC, an inductor passes DC, blocks AC. So what are the main uses of inductors? Well, inductors are used in quite a lot of ways, but there are at least three main purposes for them, if you like. Yeah, I'm sure there are others you can think of. Guys, comment. But these are the basic ones we should learn first. So the first one is it's used as a filter. This takes advantage of the fact that it will pass DC and block AC. And just like the capacitors, depending on the value of the inductor and the frequency of the AC, it will respond in different amounts, if you like. Its resistance to AC increases with the frequency of the AC, okay? Whereas with capacitors, the resistance to the AC decreases with the frequency. Yeah, so opposites again. Because the resistance varies with frequency, we don't call it resistance, by the way, we call it impedance. And there's another term which is related to that called reactance, and we'll talk about this in the next video, the difference between these, and we'll do a few more experiments. But the most likely ways you're going to see inductors used, well, one is a filter to remove noise, ripple from a DC signal. So common circuit, you'll have capacitor connected to ground. This is some sort of voltage or signal. Let's say it's a power supply voltage, okay? So we know that the DC will come through and the AC will go through here. Then quite commonly you'll find an inductor. So what's happening now is this is allowing the DC to go through, but this effectively is blocking the AC. This is taking AC to ground. We'll find another capacitor going to ground again, so whatever's left goes down through there in the way of AC, and coming out of here it's a nice smooth DC signal, or voltage. So that's one of the very common uses. The other one, well, this is a lot dependent on this thing we were just looking at with the high voltage on the relay. By the way, this high voltage has got a name, it's called back EMF. Okay, that's the high voltage where it builds up the potential until it finds a current path. Okay, that's what it's actually called. Now we saw that energizing the relay coil and then opening the switch caused a very high voltage to come out. We can take advantage of this and we can use this effectively to generate any DC voltage we want from another DC voltage. So imagine we have a coil, okay, and we apply a voltage through a switch, okay, 12 volts let's say, okay, and we can control the switch electronically, so we can switch it on and off for very short periods of time. Okay, what we can do now is apply the voltage for such a short period the coil never fully magnetizes, so basically nothing comes out at this end. And then when we open the switch, whatever amount of charge we put into here will generate an output voltage, just like we saw coming out of that relay coil. And we can put a capacitor here to ground. Now, if we put a very small amount of charge into our coil, it's current, we put a small amount of current in, and then we switch it off very rapidly. When the field collapses, we'll get a small amount of voltage out. If we have the switch closed for a little bit longer, I'm talking microseconds, very short periods of time, it's closed for a little bit longer, we can get a bit more voltage out, and we can close the switch for a little bit longer again. So effectively our switch is closing for short periods of time. This is the close. I'll draw it the other way, it looks better. Our switch is applying 12 volts, very short bursts. Each time this goes back to 0, the field will collapse and we'll get some voltage in here, and this will give us whatever voltage. If we then start to have the switch closed for just a little bit longer, yeah, you can see each time it's closed we get a bit more current in here, so we get a bigger magnetic field, and when it collapses we get more voltage in there. And if we can make a circuit that monitors the voltage here and uses that voltage to control the time that switch is open and closed for there, we can make a regulated supply that will keep the same voltage on there regardless of however much power you're drawing from it. If you draw more power, the voltage would tend to drop because you're using the current, and we can monitor that and make the switch stay closed a little bit longer to increase the magnetic field. So that is a very common type of circuit, especially in modern electronics. We'll see this a lot later, okay? And the third main use is what are called tuning circuits. So with a tuning circuit, we take a coil and we take a capacitor, like so, okay? We apply some voltage to charge this capacitor, and the capacitor is now charged, positive, and then we take the voltage away. What happens? Well, the capacitor will discharge via the coil, and by doing so it builds up a magnetic field in the inductor, the coil. But the capacitor will rapidly discharge, so there's no more charge in the capacitor. At this point the current stops flowing into the coil. We already know what happens. The coil then generates the high pressure at this end and pushes a positive voltage out and charges this end of the capacitor. So this end of the capacitor is now positive. But the magnetic field will collapse to the point where there's no more current coming to the capacitor. What happens now? Well, the capacitor will discharge via the inductor, build up a magnetic field, but the capacitor will discharge. So the inductor then field collapses and it charges the capacitor back that way. So we can see that this capacitor is alternately charging positive on one end, positive on the other end, okay? And the rate at which it's doing so depends on the value of the capacitor and the value of the coil. And for a given value of capacitor and coil, this will give you a fixed frequency of oscillation, okay? And this is called a resonant circuit. It's like a tuning fork or a bell. You hit a bell with a hammer and it will ring at a certain tone, and the tone will depend on effectively the size of the bell, the weight, and a few diameter and whatever affects bells. I'm not a campanologist, but I can understand how it works, and I'm guessing you can as well. So this is called a resonant circuit. You might think that you could effectively put some power, charge the capacitor, take the power away, and this will continue to resonate forever. It won't, because there's resistance in the winding, okay? So effectively the resistance is like friction. Eventually the oscillations will go down to zero. But if you can create a circuit where you continually apply a pulse of power, this is like hitting the bell with a hammer again. You hit it once, bong, and then it goes and you hit it again and it'll do the same, yeah. And if you just keep hitting it, it doesn't really matter what speed you're hitting it at, you'll still get the same tone out of the bell, and that's what the resonance circuit is doing. These circuits are used for two main purposes. One is to generate a signal at a certain frequency, and the other one is to extract a signal at a certain frequency out of a more complex waveform with lots of frequencies. This is why it's called a tuning circuit as well. So, for example, if you had an antenna receiving lots of radio stations on different frequencies, this circuit can pick out the one you want by changing the value of the capacitor. You can change the resonant frequency, and this will always resonate at the same frequency. And if you set the resonant frequency correctly, you'll receive the correct radio station because they're on different frequencies. Okay, so we'll play around with a bit of this on the next video, and then I think we can say that inductors are done. Anything you'd like me to add to this little tutorial on inductors? Now's the time, down there, and I'll see you all soon in the next part. Ciao for now, guys.